Welcome back, Leo Lions. This is Mrs. Morgan with today's lesson on classifying real numbers. So everything we're going to talk about in algebra, number-wise, are going to be real numbers. There is a set of imaginary numbers, but you talk about those when you get into Algebra 2. So that's why when I say classifying real numbers, that just means all numbers that we're dealing with in algebra class. So let's first look at this example. Over the summer, Ethan spent a week at camp. Ethan met several campers, including those from different states, to those that ended up being in some of Ethan's classes at school. The categories listed below describe the types of campers that Ethan met in no particular order. We're going to use the graphic organizer to the right and place the letter of each category where we think it belongs. So if you look at this graphic organizer, it includes all the friends from camp. On the right side, there's one box all by itself. Just an empty box there. On the left side then, there are a whole bunch of boxes within boxes. So if we have to categorize these 5 things and put them into the graphic organizer, first let's think about how do we just separate them into 2 categories. So we have same city, same state, same class, same school, and then out of state. So the 2 different categories here, the 2 opposites are they from the same state or are they from out of state? So everything else, if they're in the same school, if they're in the same city, the same class, they're all in the same state. So that's kind of where all those boxes on the left-hand side are inside of each other. That's all going to represent that they're from the same state. And then the other side is, well, then those are the out-of-state people. Okay, those are the 2 different categories. So same state, and then everything over here, they're out of state. The boxes within boxes means that this box in the middle here, okay, that box is inside all the other boxes. So that means if they fit into this category, then they also fit into this category and this category and that category, okay? If let's say they fit into this box, well, that box is within the next box and the next box and so on. So that's how we can use this graphic organizer. If they fit into one category, well, they can also fit into several categories, okay? And keep in mind, the entire graphic organizer is friends from camp. They all fit inside the big box, okay? So we have, let's see, same state and out of state is what we separated those 2 boxes into. So next would be the next specific thing. So we have same city, same class, same school. So the next one, same state, and then this is same city. So we're going from least specific down to most specific. Here they could be from the same state, but they may not be from the same city. So if they fit into this box here, we'll notice that box isn't inside the other boxes. So it would just fit into that category of same state and then the category of friends from camp, okay? Now, let's keep going down. We got the same city taken care of. The next specific would be same school. And then same class. Okay, and this is showing that if they fit into this box in the middle here, if they're from, same class. If they're from the same class, well, that means they're also from the same school, they're also from the same city, and they're also from the same state. So they can fit into all those categories. Okay, and we're going to use a graphic organizer like this with all of our different types of numbers. Okay, so Ryan is one of Ethan's camp friends who is also in his first period class. So list all of these sections of the graphic organizer that Ryan's name could belong to. So we just talked about that. If they're from the same class, and off to the right here, I'm just going to use the letters identified. So same class is B. Well, then that also means that they're the same school. So same school was D. That also means they're from the same city, which is A. And then that also means they're from the same state. So that was C. So they're from all of these categories. Now, which would be the best section to place Ryan's name in? Well, the most specific is B, the same class. So I'm going to say B, same class, is the best section because it's most specific. Oops, sorry. Going all over the place here. So same class because it's most specific. Okay, now let's look at our definitions of some different types of numbers, and then we're going to organize them into a graphic organizer. So we have natural numbers, the set of all positive counting numbers, numbers on a number line, starting with 1. Last year I started counting with my child about this time, and now he can count 1 through 15. For a 2-year-old, I feel like that's pretty good. But when I started teaching my son how to count, I didn't start with 0. That's not natural. I didn't say, hey crew, let's count. Let's say 0, 1. No, that's weird. We start with 1. So 1, 2, 3, 4, so on, so on. So those are our natural counting numbers, okay? So let's give some examples. I'm going to give even some bigger ones, something like 42. Maybe not be natural for me to count to 42 with my son, but it's 1 to infinity is our natural numbers. We may see it as a fraction, maybe something like 50 over 2. Well, 50 over 2, 50 divided by 2 is 25. So that's a natural number. Okay, and I'm even going to go larger and say something like 820. Okay, it's 1 to infinity. Down here underneath natural, I'm going to write counting to help you remember those numbers. Okay, whole numbers then are all the counting numbers, or all the natural numbers, but we're going to add in 0. So the only difference between natural and whole is that number 0. Okay, so again, I'm going to give you some examples. I'm going to give you 0 as an example. I'm going to give you a square root example. So the square root of 100 is 10. 10 is a whole number. Okay, maybe something like 4 plus the square root of 4. So the square root of 4 is 2. So 4 plus 2 is 6. That's a whole number. Okay, we cannot have decimals in these unless it represents a whole number. Okay, integers are the set of whole numbers and their opposites. So that means it includes the negatives. Okay, so let's say negative 15 over 3. It looks like a fraction, but if we simplify it, that represents negative 5. All right, 25 as an example. Negative square root of 81. That would be negative 9. So not always are they just perfect whole numbers. You may have to simplify them and then see that they're whole numbers. But integers only include whole numbers. Okay, positives and negatives. Rational are any number that can be written as a fraction. That's the best, easiest definition I can give you. So terminating decimals, repeating decimals, those can be written as fractions. And then square roots of perfect squares. So if they come out to a whole number, that's what a perfect square is, then it's a rational number. So for example, now we get into our fractions and decimals. Let's say 12 and 5/7. Okay, it would be a rational number. Negative 6.8 is a rational number. It terminates. It can be written as a fraction. And then let's give you a repeating decimal, 5.3 repeating. Could be written as a fraction, so it's rational. Okay, irrational is just the opposite definition then. Numbers that cannot be written as fractions. Okay, so non-terminating decimals, meaning they do not end. Non-repeating, so they cannot repeat. And then square roots of non-perfect squares. So any square root that does not come out to a whole number, it's irrational. Okay, so let's look at an example. One of the most common examples is pi. Even if we take a number and multiply it by pi, it's still going to be an irrational, so something like 3 times pi. The square root of 10 does not come out to a perfect whole number, so it's irrational. And then let's do a decimal that goes on and on forever, but it does not repeat. And then that is also irrational. okay? Now, let's organize these into a graphic organizer, because if they fit one category, they may fit more than one. So in our real numbers here, remember, real numbers are all numbers we're talking about. We've got two different categories. We have rational and irrational. Rational can be written as a fraction. Irrational cannot be written as a fraction. Okay? Next then, if we want to be very, very specific, let's go towards the middle. This may make more sense. I'm going to start with the counting numbers. That goes in the very center, because if it fits into this category, if it is 1, 2, 3, 4, 5, 6, so on forever, well, then it's also a whole number. It's inside that box. It's also inside the next box. It's also an integer, a positive whole number, and it's also a rational because we can write it as a fraction. So if it is a natural number in the middle there, it fits all of them, okay? If it's a whole number, 0 is the only difference there between those, well, then it's also an integer, it's also rational, okay? And all these numbers fit into the real number category, okay? So let's look at our examples here. 2 times the square root of 64. So remember, the square root of 64 is 8. So this really means 2 times 8. So we're categorizing the number 16. Okay, 16 is a natural counting number. Now when we write this example down, we're going to write it how it was given to us. 2 times the square root of 64. Okay, negative 15. Negatives are not in our natural or our whole. Integer is the first time that we bring into negative numbers. So negative 15 goes in the integer category. 16 over 4, so 16 divided by 4 simplifies to 4. So we're categorizing the number 4. It's a natural counting number. So 16 over 4 goes here. The square root of 75 does not come out to a perfect square root or a perfect whole number, so that is in our irrational category. All right, 0. I already threw that one on here because that's the only difference between natural and whole, so the 0 goes in the whole number. Negative 12.2. Okay, natural, whole, integer are all whole numbers. We can't deal with decimals. So the best category we can put it in here is the rational, negative 12.2. Okay, so let's look at these next examples. We're going to identify all the categories and then circle the most specific set. Okay, so 12 pi, anything with pi in it, unless it were like something, maybe pi over pi. Well, pi divided by pi is going to be 1, so you got to be careful. But if we're multiplying anything by pi, it's still going to turn out to a big, long decimal that doesn't repeat. So 12 pi is an irrational number, and then it also fits in the big overall box of real. Now, the most specific would be irrational, okay? Square root of 30 does not come out to a whole number. It's a non-perfect square root, so it is irrational as well and also fits the real category. The most specific would be irrational. 45 over 5, that simplifies to 9, so remember we're actually categorizing this number 9. So that's a natural counting number. It's a whole number. It does not have a decimal. It's an integer. It's a rational because you can write it as a fraction. 9 can be written as 9 over 1 and also fits our real category. The most specific would be that smallest box, the natural. Okay, negative square root of 64, remember that would simplify to negative 8. So the first time negatives introduced in our graphic organizer is integer. So it fits integer, it fits irrational, we can write it as a fraction, and it also fits real. Maybe. Uh-oh, I lost my pen here. There we go. I knew it'd show up on me. All right, sorry about that. So this is also real, and integer is our most specific. Okay, 50.75. Remember, natural, whole, integer all have to be whole numbers, no decimal. So this best category would be rational. We can write it as a fraction. Remember, 75 hundredths. So that's rational and real. Most specific would be rational. Okay? Then let's look at these last four. An irrational number with a value greater than 10. Irrational number, let's pick a number greater than 10. Let's say 11. If we have something like 3, 4, 3, 4, 4, 3, 4, 4, 4, and so on, there's a pattern, but there's not a specific number or a group of numbers that are repeating over and over. So that would be an irrational number, and it's greater than 10. Okay, an integer between -5 and -6. We're looking for an integer. An integer has to be a whole number. Well, can we find a whole number in between -5 and -6? That's not possible, all right, because we're only going to have decimals. So this example is not possible, and we explained why right here, because an integer has to be a whole number. Okay, a whole number less than 0. So it has to be a whole number. Remember our definition on the other side, whole number, the set of all positive. So it has to be a positive number. So a number less than 0, we're going to get into the negatives. So this is not possible. Because whole numbers start with 0. All right, and last one, a rational number represented as a square root. So you could pick any perfect square root. Let's say the square root of 144, that equals 12. So as long as it comes out to a whole number, that is a rational number as a square root. All right, awesome job. Thanks.